In this video, we want to begin discussing how to construct a sample space and how to get some of the other probabilities that we look at. So in example 4 here, we want to use a tree diagram to find the sample space for the gender of 3 children in a family. So a tree diagram, basically we start off with the possible outcomes and then we branch off from there. Okay, so let's think about, this is the first child. Here's our second child. And then we're going to branch off from there for the third child. Now you'll notice I'm drawing 2 lines because what are the possible outcomes for the first child? Well, it's a boy or it's a girl. The second child, if I got a boy the first time, doesn't matter because I could still get a boy or a girl the second time. And same thing with the third child. I could have a boy or a girl, even if I had 2 boys already. If I had a boy then a girl, I could get a boy or a girl. If I had a girl the first time, my second child could be a boy or a girl. And my third child could be a boy or a girl. A boy or a girl. So notice that whatever happens on the first one doesn't change my possible outcomes for the second one or the third one. Whenever I want to actually construct the sample space, what I'm going to do is I'm going to follow each one of these lines. So my first possible outcome is to have 3 boys. My second possible outcome is to have 2 boys and then a girl. My third is to have a boy, a girl, and then a boy. I could have a boy, a girl, and then a girl. I could have a girl and then 2 boys. So a girl, boy, boy. I could have a girl, a boy, and then a girl. So a girl, boy, girl. Or I could have a girl, girl, and boy. Or I could have 3 girls. So I actually have 8 outcomes in this sample space. And these are the different possible outcomes for that sample space. So this is just using a tree diagram to find the possible outcomes. Let's look at whenever we have sampling involved where it's not necessarily equally likely anymore. So in a national survey conducted by the Centers for Disease Control to determine college students' health risk behaviors, college students were asked, how often do you wear a seatbelt when riding in a car driven by someone else? So in other words, you're in the passenger seat, you're in the back seat. How often do you wear your seatbelt? The frequencies appear in the following table. So 125 students said that they never wear a seatbelt when someone else is driving. 324 say that they rarely do. 552 say sometimes. 1,257 say most of the time. 2,518 of the students said that they always wear a seatbelt while someone else is driving. Whenever you're looking at this type of table, we need to find our N, our total number. Just like when we worked with frequency distributions and everything else, we've got to find that total possible number, okay? So how we do that is we just add up these frequencies. We take 125 plus 324 plus 552 plus 1,257, 2,518. And we get that there were a total of 4,776 students surveyed in this particular example. A surveyor selects a single student at random from this population, so from this group. What is the probability that the sampled student wears a seatbelt most of the time? So the probability of them answering most of the time, we are going to take the total, 4,776, for our denominator, and then we're going to look up here, most of the time, there was 1,257 students that said most of the time. Now we can attempt to simplify this fraction. In all honesty, most of the time we're going to look at it as a decimal. And so if I divide this out, I'm going to get 0.2632, which is good because it is between 0 and 1 on my scale. The probability the sampled student wears a seatbelt most of the time is 0.2632. Now you'll notice I have not changed this into a percentage or anything like that. I just took the straight division and worked from there. Now, sometimes we need to talk about unusual events. So an event is what we consider unusual if it meets the following criteria. The event is not likely to happen. That means that it has a probability that is extremely small. Unfortunately, there is no hard, fast rule to determine this. What we do most of the time for most of our probabilities and research, events with a probability of less than 0.05, then it is considered to be unusual. This is one of those cases. It depends. If you're in medical research, that probability gets smaller because you want to have a larger confidence. But as a general rule, 0.05 or 5%, if it has a probability of 5% or less, then it is considered to be unusual. So let's look at an example of how we would determine this. We want to continue with the college survey. Would it be considered unusual for a student to answer they never wear a seatbelt? Well, here is our never. And recall that we had a total of 4,776. So the probability that a student answers they never wear a seatbelt is going to be 125 divided by 4,776. We divide this out and we get 0.0262. For us to consider if it's unusual or not, we compare this number to 0.05. So if I look at a number line, here's 0, here's 1, here's 0.05. 0.02 is going to be somewhere about right here. If it is anywhere in this area right here, then it is considered to be unusual. So since the probability is less than 0.05, 5/100ths, then by the most commonly applied rule, that's that one that we use most of the time, some disciplines will decrease or increase this value. It is unusual for a student to answer they never wear a seatbelt. So again, we're looking at, is it 0.05 or less? When we want to approximate probabilities with what we call the empirical method, which is very similar to what we've been doing. So the empirical method consists of repeating an experiment a large number of times, thousands of times or something, and using proportion of times an outcome occurs to approximate the probability of the outcome. What we just did with the value divided by n is the same type of thing. So let's look at some notation again. So there are 100,000 voters in a city. This is your capital N, your population size. A pollster takes a simple random sample of 1,000. That is our lowercase n, our sample size. And they find that 513, that's our K, support a bond issue to support the public library. And 487, this is our K for opposition. Remember, this is our K for support. Estimate the probability that a randomly chosen voter in this city supports the bond issue. So we're talking about these people right here. So the probability that we support it, we had our K, which is 513, out of our sample size, not out of our 100,000, it's out of just our 1,000 voters. And when we divide this out, we get 0.513, or 513 thousandths. So the probability that a randomly selected voter in this city supports the bond issue is 0.513. The biggest thing to remember about probabilities is if you have values, you have your sample size and you have how many outcomes in that sample size occur in your event, you're going to take the number of possible outcomes divided by the total number of outcomes. So I'd like for you to practice some of your basic probability rules, look at the tree diagram with the sample sizes, determine whether an event is unusual or not. That's the 0.05. And then let me know if you have any questions.